You know, sometimes the biggest secrets are hiding in the simplest places. What if I told you that inside a single ripple of water, there's a mathematical mystery? One so deep it took science more than 100 years to figure it out. It's the secret of a wave that could theoretically live forever.
I mean, that sounds impossible, right? Waves are supposed to break. They spread out, they lose energy, they disappear. That's just what they do. But what if there was one special kind of wave that didn't? This whole story is about a scientific puzzle that didn't start in some high-tech lab, but on a quiet canal in Scotland.
Okay, so let's set the scene. We're going way back to 1834. An engineer sees something that, according to the physics of the day, just should not be possible. Picture this. An engineer named John Scott Russell is riding his horse alongside a canal. A boat stops suddenly, and it pushes this single perfect hump of water forward. Now, he expects it to flatten out in a few seconds, but it doesn't. He actually starts chasing it on his horse and follows it for more than a mile as this perfectly formed wave just keeps on going, not losing its shape, not slowing down. He called it the wave of translation, and for decades, nobody in science could explain it.
And the road from just seeing this thing to actually understanding it was, well, it was long. It took over 60 years just to get an equation to describe it, and then another 70 years after that for technology to finally catch up and show us what was really going on.
So the first huge piece of the puzzle falls into place in 1895. That's when two Dutch mathematicians finally managed to write down the mathematical recipe for Russell's perfect wave.
And here it is, the Korteweg-de Vries equation, or KdV for short. Now, whoa, don't worry about all the symbols. You don't have to solve it. The really important thing is what it describes. Think of it like a mathematical sentence that says this special wave can exist because of a perfect, delicate balance between two forces that are trying to do opposite things.
And this balances everything. See, on one side, you've got a force called nonlinearity. That's the thing that makes waves get taller and steeper until they eventually break. On the other side, you have dispersion. That's the force that makes waves spread out and fade away. Well, in the KdV equation, these two forces are locked in a perfect tug-of-war. One can't beat the other, so the wave can't break, and it can't spread out. It's just held there, in this perfect, stable shape, forever.
So scientists had the recipe, they had the equation, but they had absolutely no idea what it was truly capable of. It was like they'd been handed a key, but they had no clue what incredible door it was meant to unlock. That discovery, well, that had to wait for the computer age.
All right, let's jump forward in time, way forward, to 1965. Two researchers, Norman Zabusky and Martin Kruskal, decided to dust off that old KdV equation and feed it into a modern computer, just to see what would happen.
Their setup was pretty simple. They just programmed in a basic smooth wave, like a sine wave, and then hit go. They just let the computer run the simulation and let the rules of the KdV equation play out.
Now, based on everything they knew about these kinds of equations, they were expecting a total mess. They thought the wave would quickly break apart into a chaotic jumble. But that is not at all what the computer showed them.
The simulation showed something completely astonishing. The wave didn't dissolve. Instead, it neatly split into a whole parade of these individual, perfectly stable humps, looking just like the one John Scott Russell had chased on his horse. Each one was its own perfect, solitary wave.
Zabusky and Kruskal realized they were looking at something new, something that needed its own name. So they took the word solitary and added the on you see on particles like electron, and they called them solitons. But naming them was just the start.
This is the part that is just mind-blowing. The truly shocking discovery was what happened when these solitons ran into each other. Normal waves interfere, right? They add up or cancel out. But solitons, they passed right through one another. A faster one would catch up to a slower one, they'd merge into one shape for a split second, and then they'd pop out the other side completely unchanged. It was like they were ghosts. It just defied all intuition.
So, the huge question was, why? How is this even possible? What gives the soliton this incredible superpower? Well, the answer was hiding deep inside the mathematics. It turns out the KdV equation is part of a very special, very rare club of equations called integrable systems. And the easiest way to think about that is that the system has a kind of perfect, unshakable memory. It knows exactly what shape it's supposed to have, and no matter what, it will always find its way back.
This memory isn't just a nice idea.
It comes from an infinite number of unbreakable rules. These are called conserved quantities. So it's not just that things like mass and momentum are conserved. That's normal. For the KdV equation, there are infinitely more hidden rules that the wave has to obey, forever. This huge list of constraints is what locks the soliton into its perfect shape.
And that hidden structure is the secret sauce. It's what forces the wave to remember its own identity. After it passes through another soliton and things get jumbled for a moment, this infinite set of rules basically says, nope, you have to go back to exactly how you were. And it reforms perfectly every single time.
And what's so cool is that this discovery wasn't just some weird mathematical curiosity. It turns out that solitons are, well, they're pretty much everywhere, from the deepest parts of the ocean right here on Earth to the far reaches of space.
The same idea that started on that little canal is now used to understand all sorts of phenomena. We're talking about giant, unseen waves moving deep within the ocean, ripples in cosmic plasma between the stars, and even how vibrations travel through the atoms in a crystal. The soliton is a fundamental pattern in our universe.
And that original KdV equation, it was just a beginning. It basically became the patriarch of a whole new family of physics. Scientists started tweaking that original recipe, adding a little bit of friction here, changing a term there, to describe an even wider range of things, all built on this core, incredible idea of the soliton.
Which really leaves us with this one fascinating question, doesn't it? The whole story of the soliton started with one guy on a horse who saw something weird, and it took 130 years to fully unpack what it meant. It just makes you wonder, what other beautiful hidden rules are out there, shaping our world, hiding in plain sight, just waiting for us to find them?